We're going to start section or chapter 6 today, section 6.1. This title is so long that it will not fit when I save it on my iPad. Yeah. Verifying differential equations, often abbreviated DE. Those of you who want to take or intend to take more math classes, you might see differential equations listed as one of your math elective options or maybe one of your required options. Our math majors are required to take it. So this section is the part of Calc 2 that is the prerequisite really for that particular class. And then also finding particular solutions, which correlates and goes along with this verifying differential equations part. So first let's talk about what a differential equation is. A differential equation is an equation involving x, y, and y prime. And a solution of the differential equation is a function y equals f of x that satisfies it, that works. That's what we mean when we say a solution ever, right? Is it something that works inside of an equation? Okay, so when we verify, think way back to like the very first time you would have seen something like this would have been like a pre-algebra course. Okay, so probably like 7th grade for some of you, 6th grade maybe, somewhere in there. 6th grade, 7th grade, maybe 8th grade, okay? And they verified that something was a solution to an equation. It meant they gave you values, and you plugged them in, and you checked to make sure that both sides of the equation were equal when you were done. You guys remember that? That's really what we're going to do on this first part as well. Verifying that this is a solution means finding if it works in the differential equation. So you'll notice in the differential equation, by definition, this actually satisfies what we said it was. It's an equation involving y, x, and y prime. Right? Okay, now we've got the equation y equals here, but of course in order to plug this in we need to know what y prime is, so we need to be able to take the derivative of this particular equation. So what is the derivative of this equation? Close. It's negative 2 and then e to the negative 2x. So the derivative of e to the x is e to the x, and then this exponent, the negative 2x itself's derivative is negative 2. So these are the pieces of information that we're going to plug in down here. We're going to take our 3 that we're given. We just found y prime, which was negative 2 e to the negative 2x, plus 5 times the equation y, which was e to the negative 2x. And what we want to verify is that this will, in fact, when simplified, equal negative e to the negative 2x. So we want to clean up the left-hand side in particular to see if it equals the right-hand side. Usually, it's inappropriate to sort of move things between the sides. The whole goal is to make sure that the two sides are equal when you're done. If you're actually moving things between the two sides, you're using properties of equality, which assumes that things are equal, and that's kind of inappropriate. So we're going to try and manipulate the left-hand side or the right-hand side, but not mix them together as we're working through this. On this one, it's no big deal. If you take a look at the first piece, 3 times negative 2, you get negative 6. So this is negative 6 e to the negative 2x plus 5 e to the negative 2x. And of course, they have the same variable component, right? This piece is the same. So since those match, we can actually add them together and we end up getting negative 6 plus 5, which is negative 1, or negative e to the negative 2x, which is exactly the same thing that's on the other side. And it checks out. Simple enough? It's really a lot like pre-algebra, this component of it. Too simple, you don't know what to do. Well, we'll try and complicate it with part B. This solution's a little bit messier. Agreed? Yeah. All right, but if you'll notice, this one says it's a differential equation. It doesn't quite satisfy the same thing that I just told you that it was before, but if you can sort of extend your idea, it does. This definition says it involves x, y, and y prime. And can you imagine that if it involved y double prime, that would be okay? Yeah, it is. So the definition actually extends to include y prime. So you see that this differential equation doesn't include y prime, but it does include y double prime, right? The second derivative. So the first thing that we have to do is we have to take the solution, or the proposed solution that we're given, and we have to find y prime, not because we're going to use it, but because we're going to use it to find y double prime. Okay? So I will do this on the left side, and then I will work my differential equation over here on the right side when I'm done. So if we take our original solution or proposed solution, we have y equals negative cosine natural log secant x plus tangent x. And you should notice that this particular differential or this particular solution is of what kind of a problem? Somebody said it. It's a product. This piece and this piece are multiplied. So don't go throwing the, what's the expression? Don't throw the baby out with the bathwater. Have you ever heard that expression before? Don't forget the things that you already know. If it's a product, you're still going to have to use the product rule. Okay? So we do in fact have a product here. So the first piece when we're doing the product is to do what? At least one version of it is what? Okay, Abby wants to take the derivative of the first piece. So what's the derivative of negative cosine of x? It's sine of x. Okay, sine of x. There we go. And then what do we do, Abby? The regular second piece. So the regular second piece, yeah, okay, I'll show it to you. We're going to see something cool happen in a second. I haven't noticed my notes differently, but that's fine. So the regular second piece was the natural log of secant x plus tangent x. All right, we're halfway done. Now what? The original of the first one, which was negative cosine of x, times the derivative of the second one, which is loads of fun, because it's a natural log of something inside, which makes it a chain rule, right? Yeah? So what's the derivative when you get natural log involved? Okay, say it again. 1 over secant of x plus tangent of x. Okay, good. Multiplied by the derivative of the secant and the tangent. So what's the derivative of secant? Secant x, tangent x, good. Plus, right? What's the derivative of tangent x? Secant squared of x. Okay, so taking a look at this, we have sine x natural log of secant x plus tangent x. That's awful, right? There's some beautiful things that happen with the second piece. Does anybody see something that happens with the second piece that's friendly? Yeah, the part that's in parentheses, if I factor out a secant, what am I left with? Evan, you saw it, so what am I left with? Tangent plus secant. Why is that friendly? Yeah, that's what the bottom is, right? So this piece down here and this piece right here cancel. Not only that, but when they cancel, what are we left with? Well, cosine and secant. So what happens when you multiply cosine times secant? You get 1. Yeah? Because they're reciprocals. So this is minus 1. Absolutely wonderful. Okay, but we really didn't need the first derivative. I mean, we did, but we don't. So we need to keep going, yeah? So when you do your second derivative, it was super crucial that we simplified that first derivative because it would have been awful to find the second derivative of the mess. We have less of a mess once we've simplified. In particular, the minus 1 at the end is going to go away when we take the derivative, right? So we really only have the derivative of something that looks an awful lot like what we just took the derivative of. So we've done most of it. The derivative of sine, of course, is cosine. And then we can rewrite the second piece, so the natural log of secant x plus tangent x. And then we have plus, and then we would take the original of this one, sine of x. And we have the original piece that, or the derivative that was just like the original one we took, which is 1 over secant of x. Can I not write it? Are you guys good with the fact that it's going to be the same and I'm going to be able to simplify it to secant? Yes? All of this is going to be the same thing below, right? And we all agree it simplifies to secant. And then somebody else said something. It will, because secant is the same as 1 over cosine, right? So sine times 1 over cosine is tangent. Okay, so this is the cosine of the natural log of secant x plus tangent x plus tangent of x. All right, I definitely need more space. I should have put in a blank slide and I didn't, but we'll fix it, no problem. Okay, that was not a good idea. Let's try one more thing. That might help. Yes, indeed. Okay, now we're going to take the differential equation and substitute it into the differential equation to see that we are in fact going to solve this differential equation. So I'm going to draw a line here. Let's do it here. And we'll solve it below that line. All right, so the first piece says I'm supposed to take the second derivative. That's the final thing that I just wrote down, correct? So this would be the cosine of the natural log of the absolute value of secant x plus tangent x plus the tangent of x. That's the second derivative. And it says I'm supposed to add that to the original first thing that I was given, right? Which was actually a negative cosine of the natural log of secant of x plus tangent of x. So far so good. And we're supposed to be checking that this is equal to tangent of x. So what do you see? Yeah. This and this are the same with opposite signs because we did some cool trig stuff involved in there, right? We did the derivative twice so that it came back around. And so they add to 0. And I'm left with tangent of x on the left. And of course that equals the same as the tangent of x on the right. Okay, so we got some fancy derivative stuff going on, right? Some cleaning things up with some trig and some substitution, which is a pre-algebra idea. Everybody good so far? Now, let's do another one. This says to verify the particular solution of the differential equation. So what does that mean? Well, we're going to start out with doing the same thing we did before, verifying that it's a solution. Okay? So we have a solution, we have the differential equation, and we're going to do all the same steps that we just did before. So this is a step A, B thing. We've been doing step A already, so we're going to continue as though the problem were the same, and then we'll figure out this y of pi over 2 equals 1 business and figure out what happens with that, okay? So to start with, part A, we're going to take this particular solution, and we're going to take its derivative. So what's the derivative of e to the negative? So what is y prime when we have y equals e to the negative cosine of x? Sine of x, e to the negative cosine of x, right, like that. So the derivative of e to a power is e to the power, and then the power's derivative, that is the derivative of negative cosine of x, is sine of x. So everybody good with where we got that derivative? You guys are so good at derivatives now. Aren't you impressed with yourself? You should be. You should be impressed with yourselves. Okay, and then we're going to verify that it actually works into the differential equation. The differential equation says that I'm supposed to take the derivative. Well, that's the sine of x, e to the negative cosine of x. And it's supposed to equal y. Well, y was the original function, which was e to the negative cosine of x, times the sine of x. And yeah, no problem. That one was really clean, right? Especially compared to that last one. No problem. Those are the same. They're just different orders of multiplication. Multiplication is commutative, no problem. Okay, so part B then says where pi over 2 equals 1. So what does that mean? Well, we're just making sure that we have that particular solution, y equals pi over 2, y of pi over 2 equals 1, works in the solution that we were given. In other words, we're doing another step of substituting. We're taking this and we're plugging it into this to make sure it actually works. This particular value is actually on the solution that we are given. So we're going to verify that y of pi over 2 into our equation y of x, so that's equal to e to the negative cosine of pi over 2. And what we want to verify is that really, in fact, is going to be the value 1. So what is the cosine of pi over 2? It's 0. And then, of course, a negative 0 is the same as 0, right? So this is e to the 0. And what is anything to the 0 power? 1. So step B is simply plugging in the point that we're given into the proposed solution that we were given. What do you think? It's doable, right? Now, have you seen this notation before? I don't know if you have or not, because I can't remember if I always teach it in Calc 1 or if it shows up in some. It shows up in some books, but not all books. Have you ever seen that 4 in the middle of the arrow thing going on? It is. It's the fourth derivative. So, you know, we do second derivatives, we just do the double prime. If you do third derivatives, it's okay to do the triple prime. But once you get to the fourth derivative, I mean, really, you're going to do like 4 little primes in the air? Not usually. So anything bigger than, sometimes even bigger than a second derivative, but certainly bigger than a third derivative, you'll see this little piece up in the air. It's in parentheses, so as not to confuse you with powers, okay? Always in parentheses, and it means the derivative. So this right here is saying that we have a fourth derivative. Okay? So this says that I need the fourth derivative of y minus 16y to equal 0, and we're verifying or determining whether this particular function is a solution. Well, I'm going to need the fourth derivative, right? Good thing is there's no products, there's no chain rules, there's nothing. This is a very clean fourth derivative. So let's take a look. What would y prime be? Derivative of 2 sine of x. 2 cosine of x, that's right. And then what would the second derivative be? Negative 2 sine of x. Right, they just go back and forth, sines and cosines. I'll use the third notation like this. What's the third derivative going to be? Negative 2 cosine of x. And then the fourth derivative, that's when we'll put that notation in with a 4, would be what? 2 sine of x. And we're back to the beginning, aren't we? We are. So this happens, right? We've got this cyclic nature of things. And we're trying to decide if it's going to equal this. Now notice the directions changed slightly from the last 3 problems. The last 3 problems used what word that this one lacks? Nope. What was the first word of the directions for all 3? Verify. What does verify mean?
Check it.
Check it. It means it's really going to work, right? You're not really, be careful, right? Because that's useful information. If it says verify, and you find out somewhere along the way it doesn't work, you've made a mistake. Because it's supposed to work. That's what verify means. Verify that it works. This one doesn't say verify. What does it say? Determine. What does determine mean? It might not work. Okay? So if you look at the word determine here and you're thinking verify and you find that this doesn't work, you're probably going to be really anxious and worried. Because it didn't work. But that's what determine means. It might not work. Okay? All right, so we're going to see if this works now. It says fourth derivative, so that's the 2 sine x that I just got as the very final step. Minus 16, and then the y value that we were originally given was 2 sine of x. So what happens when I have 2 sine of x minus 16 times 2 sine of x? You're not going to get 0, right? You're going to get, in fact, negative 30 sine of x. And there are locations, of course, where this does equal 0. But it's not always equal to 0, which is the goal. This does not always equal 0. So this does not work for all x. It does work for some x. Can you give me a value of x for which it would work? Sine of a value times negative 30 equals 0. 0. It works for 0. Yeah, if you plugged in x equals 0, this actually would work. But it doesn't work for every value of x, which is the goal. Okay? What's that? Yeah, it does sometimes equal 0, but it doesn't work for all x equals 0. And because it doesn't always work, it's not a solution. So therefore, y equals 2 sine of x is not a solution of the end. You can put DE. Okay, that is a typical notation for differential equation, DE.
Is there a certain notation to write for like when this is not
Not necessarily, not that I know of for an all x. I mean, the kicker is that it's the for all x down here. Do you guys know how to write for all in mathematical notation? Nope. It's an upside down A. You might have seen that before. So if you do go on into any further math classes, you'll see more and more notation, but that's one of them you see is for all x. Yeah. Yeah, it kind of does look like an ice cream cone without the ice cream, right? Okay, now, change in directions again. What does this one say we're going to do? Find. We're not verifying, we're not determining, we are finding something now, and that is slightly different. What is different in terms of the information you're given? You're given a point. What else? There's an x and a y, but there was an x and a y before. So what's a little bit different about this x and y then, Hannah? They're on the same side, and what's on the other side? A c. Well, that's not happened before, right? It's just a constant. And the thing is that when we are going to have to actually check to see that, or, well, that's not a true statement. If we were checking to see if this works at all, we would actually have to take the derivative, plug it in, and all that good stuff. And the constant part, the plus c on the other side, would go away, right? So if you were taking the derivative of 2x squared minus y squared equals c, the c on the other side would go away. Agreed? Okay. So what we're going to do to figure out if this is to find the particular solution is to take the point that we are given and plug it in to find C. Yeah, you know, it randomly does that, and I'm thinking that there's something weird that I can't figure out how it's even possible. And here's the reason. I save them as PDFs, right? And the whole point of a PDF is that I should be able to print it out anywhere on any computer and it looked exactly the same. But it doesn't always do that. Yeah, but see, it shouldn't matter on the typography. That's why I save it as a PDF. So I don't know. Yeah, but this happens, Abby, in my other classes too. Random things turn into like Egyptian characters and stuff like that. I don't know. Yeah, just change it so that it looks like this one. Thanks. Okay, we're going to plug in the point 0, 3, and we're going to solve for C. So if I plug in 0, 3, what do I get? Yeah, 2 times 0 squared minus 3 squared equals C, so C is -9. So the particular solution is 2x squared minus y squared equals -9. That's it. Finding the particular solution is this, because they tell you the general solution is this piece. You're not verifying it, you don't have to confirm it, nothing like that. They've told you. This is the general solution. And it includes the point 0, 3 if the C value is the right value. So you're just finding the correct C value. Easy enough? Yeah. No problem on that one. Now, this is different. Yeah, you don't even have to use the differential equation that they're giving you because they tell you it's a solution of it. It is a general solution. But it's different on the next problem because what does the next problem actually say? Verify. So this one you have to verify and find the particular solution. So this is like a combination problem of the first problems we did, the verify problems, and the last problem we did, the find the particular solution problems. So it doesn't really matter which order you necessarily go in always. But you're going to have to actually plug in the simplified solution eventually in a minute or two. So we're going to need a y prime and a y double prime. Agreed? Because the differential equation has a y double prime in it. So what we're going to do then is we're going to take the derivative. So what is y prime of c1 plus c2 ln x? C2 over x, right? The derivative of C1 and C2 are constants. Everybody good with that? And the derivative of a constant by itself is 0. So C1 goes away initially. C2 is a constant multiplier, so it tags along for the ride, C2 there. And then the derivative of the ln of x is 1 over x. If you prefer, and it's kind of helpful in the next step, we can rewrite this as C2x to the negative 1.
Can you plug in the y prime they give you?
The y prime equals this piece right here. You can, and we will eventually somewhere along the way, whether we do it now or do it later, yes. If you want.
We gotta solve for C2 right there.
You can.
1/2.
You can. We can also take the second derivative and use those pieces of information generically. That's how I'm going to show you to do it because we're going to solve it for it eventually somewhere anyway. But you don't actually need to know what the C1 and the C2 are to make this work. So I'm going to do it with the verify first. I'm sort of going to do it in the order of the directions of the problem, the verify part all by itself, and then the finding part second. But if you do it in the other order, it's not going to hurt anything. Okay? What would y double prime, second derivative, be? Yeah, or x to the negative 2, either way. So negative C2 over x squared, or negative C2 x to the negative 2. And I'm going to plug those into the second, or into the differential equation. So the differential equation says that if I take x and I multiply it by y double prime, which is what I just found, which is negative C2 over x squared, plus, and then I plug in y prime, which I found earlier, which is C2, oops, I'll write it as a fraction since I wrote the other one that way too, C2 over x, that this should equal 0. Does it?
You're going to have negative C2 over x plus C2 over x.
Yeah, so it works, right? Does the left-hand side and the right-hand side equal? Yep, sure does. So I've done the sort of part A stuff of the verifying part. So I'm interpreting this kind of like saying A is verify, and then it says B is finding the particular solution. So this general solution does, in fact, work for our function. Agreed? Okay. Now we're going to find the particular solution. Again, you could have done it in the other order, but I just went with the order they gave me in the problem. So to find the particular solution, it means that I'm going to use the pieces of information I was given. I am given information about y and y prime and x, which means using the y double prime won't be part of my process, correct? Okay, but y prime must be part of the process in order to find two variables. I'm supposed to be finding, or not variables, but constants. I'm supposed to be finding C1 and C2. So if I used only the original general solution and I plugged in the x value and the y value, I couldn't find both C1 and C2 at the same time. Do you know what I'm saying? That's why they have to give me information about the derivative as well on this one. I need two equations if I'm going to find two unknowns. It's the only way that's going to work. So I'm going to start with the derivative equation that I found, that you guys found with me, which was C2 over x. And it says that the y double prime is supposed to be 1/2 when x is equal to 2. Right? Y prime is 1/2 when x is 2. So what is C2 going to equal? 1. Which means I can take the original general solution, which said y equals C1 plus C2, which was now going to be the number 1, natural log x, and I can plug in the C1, or C2, which is 1. And now I can use the other information that I was given for my particular point, which says that when x is 2, y is 0. Right? When x is 2, y is 0. So what do we find that C1 is equal to? The negative natural log of 2, which is a totally fine number. There's nothing wrong with it. It's irrational. But when I write down my solution, it will look just like a negative natural log 2. So my general solution, y equals, is negative natural log of 2 plus the natural log of x. And you can leave it like that. There might be a little bit cleaner way of writing it. Any ideas?
You can combine the 2 and the x.
You could. Do you know how you could do that, Abby?
Well, since the natural log of 2 is negative, it would be a subtraction, so it would be natural log of x
So you could rewrite it as the natural log of, I said it wrong, you said it right, x over the 2. Because the negative is on the natural log of 2, which would be in the denominator. So it doesn't matter to me which form this is in, but just to be aware that if WebAssign tells you you need to simplify further, or if you're checking the back of the book, there's alternate versions of this. No, because we weren't taking any antiderivatives. And the absolute values come in when we did antiderivatives. Yeah. Good question. All right, next one. Directions changed a little bit again. It says use integration to find general solutions. We haven't found general solutions yet, right? Every problem so far has given us a general solution. Now we're going to find general solutions. Well, finding general solutions means that we're going to find antiderivatives. Okay? So as you're taking a look at this right now, it gives you a y prime. Y prime is equal to x cosine x squared. Everybody good with that so far? Okay. So what we're going to do is we're going to take an antiderivative. That is, we're going to take an integral of both sides. Now before we do that, it is more helpful for this to be written in a more convenient form that looks something like this. So what did I do? Yeah, I just multiplied dx to the other side. That okay? Sure. And what we're going to do next then is we're going to do an integral on both sides. Okay? What is the antiderivative of dy? It's y. My Calc 1 students just learned that last week on their gateway. Yeah, they weren't so sure. It is just y. Now, technically it's y plus c, but we'll get the plus c at the end. Somewhere in the end, we're going to have to put a plus c. We only need to put it one place, so we'll do it at the end. On the right-hand side, now, here's the cool thing. You ready for the cool thing? This is chapter 6. Chapter 6 comes before chapter 8. In chapter 6, the only tool you had for doing antiderivatives was what? U substitution. So your antiderivatives in this section should be things that are going to be very easy for you at this point, because you're really good at U substitution, right? You are. What would U be in this problem? X squared, what's du? 2x dx, which is a dividing by 2. So on this antiderivative, you have a 1/2 integral of the cosine of u du. That's what you have. What in the world is the antiderivative of cosine of u? Sine of u. And you have a plus c, so we'll go ahead and put the plus c in at this point. But you know that u is x squared. So we have 1/2 sine of x squared plus c. Nice, right? Yeah, really nice. Oh, that is the only way to do it. But you guys have lots of other things that you know at this point. When you see a product, it might be U substitution, it might be integration by parts, it might be, but it's not, because this is chapter 6, right? Yeah. All right, we've got one more in this section. Same directions, integration to find a general solution of the differential equation. What's our first step? Move the dx is the first step, okay? First step is always to move dx. Okay? And then integrate. So we're going to do the script s on both sides. The integration's simple. On the left, we're going to get y. That's kind of our whole goal. On the right, it is a u substitution. It's a really nice, clean, easy one, right? What would u be? Not quite. Just the negative x over 2 part. What's the derivative of negative x over 2? Negative 1/2 dx. And I don't have a negative 1/2. I've got a 5, but we're just going to keep that, tagging along for the ride. What am I going to have to do with the negative 1/2? Multiply by negative 2 to the other side. So this is negative 2 du equals dx. So this negative 2 and this 5 are going to give me negative 10. And then I have the integral of u to u. So here's negative 10. What's the antiderivative of u? I'm sorry, e to the u is what I meant to write. Thank you. Went too fast. E to the u. What's the antiderivative of e to the u? E to the u. We need a plus c here. So this is negative 10 e to the negative x over 2 plus c.
Even better news.
Uh-huh.
Multiply it by
1 over, what was that? We did. The du was negative 1/2. And so I multiplied the 5 here by this negative 2.
No, I think the antiderivative is
Yes.
have to do, because whenever you take the derivative of it, you multiply it by the derivative of it.
Yeah.
You have to do the opposite.
Right, but the derivative of e to the u is e to the u, and then you'd multiply by the derivative of u, which is 1. But dividing by the derivative of 1, e to the u, or of the u, which is 1, would also be 1. The antiderivative and the derivative of e to the x are the best ones ever, because they're themselves.